My talk is about interpolation evolutions related to Poisson-Dirichlet distributions. This is based on a joint work with Noah Feldman, Douglas Rizzolo, and Matthias Winkel. Interpolation of the interval 0, L is the collection of disjoint sub-open intervals, such that the lengths of the intervals sum up to exactly L. An example of an interpolation of the unit interval 0, 1 could be the open intervals separated by the 0 points of a Brownian motion. We are particularly interested in the family of interpolations that have the alpha diversity property, meaning that the following limits exist. In this talk, we will build interpolation valued processes that are related to the well-known Poisson-Dirichlet distribution. We can describe a Poisson-Dirichlet distribution via the stick breaking scheme. That is, we separate the length 1 into beta proportions. We keep one of them and continue separate the second one via beta proportions independently. We continue so on and so forth. And finally, we get a sequence of masses Pn, which is not necessarily decreasing. But if we rearrange them into decreasing order, then the law of the decreasing sequence will be the Poisson-Dirichlet alpha theta. On the other hand, using the sequence Pn obtained by the stick breaking scheme, we can build a random interpolation of the unit interval with block lengths given by those Pn. We construct it by any intervals inductively. So we first have an interval of length P1, then we choose to add the interval of length P2 to the left or to the right, but by a probability proportional to theta or alpha. Say we put it to the left, then for the interval of length P3, we can put it to the left or to the right or to the middle of the first two intervals. We continue so on and so forth. In the limit, we get an interpolation of the unit interval. Its law is what we call a PD alpha theta. It's worth noting that any interpolation having a law PD alpha theta almost surely have the alpha diversity property. Classical examples of PDIPs include those generated by the 0 points of Brownian bridge or the 0 points of a Brownian motion. PDIPs also appear in random continuum trees. Consider a stable continuum random tree, which is a metric space with a probability mass measure supported on its leaves. We separate it into a spine and different blocks. Here we illustrate a few. Each block contains all the off-spine subtrees that are rooted on the same spine branch point. By considering the masses of the blocks, we naturally get an interpolation such that each interval has its length corresponds to the mass of a block, and the order of the intervals are naturally given by the positions of the branch point. This interpolation is a PDIP. Interestingly, although it only contains information on the masses of the blocks, we can recover the metric information from the alpha diversity of this PDIP. By considering different tree models, we can discover different PDIPs. The main target of this talk is to construct an interpolation valued diffusion with stationary distribution PDIP alpha theta. This question is further motivated by the study of continuum tree valued diffusions, as we have seen the connection between the two objects. In our main result, we construct a past continuous strong Markov process on the space of all interpolations of the unit interval that have the alpha diversity property, and it has stationary distribution PDIP alpha theta. By saying past continuous, we mean both the blocks and the alpha diversity will evolve continuously. It is more precisely described by the matrix D alpha. This generalized previous studies for the special case theta equals to 0 and theta equals to alpha. We construct the process beta bar in two steps. First, we construct a so-called self-similar interpretation, SSIP alpha theta. Such a process beta is not necessarily interpretations of the unit interval, but it has fluctuating total mass. Next, we renormalize the process beta by its total mass and perform a Lamberti type of time change to get the process beta bar, which is what we want. In the rest of the talk, let me explain how do we construct a self-similar interpretation evolution. We use an idea developed by my co-authors and Shumik-Paul in 2019, as illustrated in this animation. We will build interpretation evolution by modeling a population in which each individual has its size evolving vertically as level y increases. We use a certain Levy process. We use its jumps to specify the birth and dies times of each individual, and this Levy process also specifies the relative positions of the individuals. Then at each level y, let's look at all the living particles at that time and put their sizes together in the order of their positions to get an interpretation. This interpretation gives the value of the process at level y. To summarize, this picture tells us to build interpretation evolution, we just need to modelize this population. That is, to specify the Levy process and mark each of its jump by a certain vertically evolving excursion. Let's first use this method to build alpha 0 SSIP evolution starting from a single interval. The initial particle will have its size evolving according to a squared Bessel process with parameter -2 alpha, and is scaled on hitting 0. The descendants of the initial particle are arranged by a stable 1 plus alpha Levy process with only positive jumps. Moreover, the size of each descendant will evolve according to a squared Bessel -2 alpha excursion. In this way, we have modelized this population, then the corresponding interpolation evolution would be the one we want. Next, to construct alpha 0 SSIP evolution starting from a general interpretation, that is to say, multiple individuals appear initially, we just need to modelize the descendants of each initial individual independently and put them all together according to the order of the initial individual. In light of this construction, we can see that alpha 0 SSIP evolution has the branching property. Finally, to construct alpha theta SSIP with positive theta, we just need to construct alpha 0 SSIP together with an independent immigration to its left. To describe the immigration, we consider the stable Levy process, the one we have used before. We consider its excursions above its running infimum. We know that these excursions form a Poisson point process, and its characteristic measure is well known. Now, mark each jump by a vertically evolving squared Bessel excursion. We know that the marked excursions again form a Poisson point process, and we can understand its characteristic measure from the one of the unmarked excursions. Now back to the construction of alpha theta SSIP. Recall that it is alpha 0 SSIP together with the immigration to the left. The immigrants will arrive according to the Poisson point process of the marked excursions, the one we have just explained before, except we will change its speed according to the parameter. More precisely, the larger theta is, the faster the immigrants will arrive. If the Poisson point process has an atom at yi, it means that the immigrants corresponding to this marked excursion will arrive at level yi to the left of the living population at that level. In this way, we have modelized this population, therefore the interpolation evolution. Summarizing, we have constructed an interpolation valued process beta, so-called alpha theta SSIP. We can further prove that this process beta is path continuous, strong Markovian, and has alpha diversity properties at all levels. Its total mass is fluctuating according to a squared Bessel process with magnitude theta. We say it is indeed self-similar in the sense that by a spacetime rescaling, we still get alpha theta SSIP. Finally, recall that we want to renormalize the process beta by its total mass and perform a Lamberti type time change to get a unit interval partition valued process beta bar. We can prove that the process beta bar expects continuous strong Markovian and it has stationary distribution p deep alpha theta. This answers the question of the talk. This is the end of my talk. The preprint of the work is available on arXiv. I also mentioned there are several other talks in this symposium related to my talk. Thank you for your attention.